Yeah, it's not a take-home test. That is, I don't. Well, that's a good question. I don't think it's a take-home test. But I was debating that when I was making your course. So let me remind myself what test 3 is. I don't think it is. No, it's not. It's not take-home. If I have a question day like that, it's not take-home. It's in class, and you don't really want a take-home test at that part of the semester either, right? I mean, they're invariably longer and sometimes harder, and it's just better not to have that. Now, it's possible test 3 might have like a take-home component. It might make sense to take a particular topic and say, you know what, that's just on the take-home or something. But that doesn't really stick out to me this semester. Ask me again when we're closer. If you made a convincing case, this topic really should be just on the take-home. But I don't know. I don't want to do that, honestly. I think that gets more work for you guys. It's just simpler to just have it a test 3. Yeah. That keeps me from asking the question that's the next thing that we haven't done, which you don't want to do. Do you want to do it? I don't know. I don't want to do it. So if I have a take-home, what I invariably will do is look at the list of homework and ask myself the question, what topic haven't we covered yet that I could actually work into the course, And so you just don't give me that option. Don't give me that option. The last time I gave a take-home test, I had a lot of complaining about the course being too much work. So it scares me. Of course, you guys don't think the course is too much work, so that's good. Before I forget. Do you guys have other questions?
I worked at 120, and you have a real eigenvector and then 2 complex ones. So when it comes to the questions of diagonalizing as a real matrix and a complex matrix, can you do both then, since it has both real and complex eigenvalues?
If it has real and if it has a complex eigenvalue, it is not real diagonalizable.
Okay.
Because the only way you can be real diagonalizable is if you can find a 3 by 3 real matrix such that it similarity transforms. We're talking about 3 by 3 matrix, all right? So you have to take your matrix, whatever it is, P inverse AP, right? And it would have to be something like lambda 1, lambda 2, lambda 3, all real. That did not happen in that problem. You said problem 120, you found one real and a pair of complex conjugate pair of eigenvalues, right? Yeah. So no, it's not real diagonalizable, but it would be complex diagonalizable, right? I mean, you could, if you put P equal to V1, V2, and V2 conjugate, if you like, or I forget if I'm using stars or bars, but stars or whatever your complex conjugate notation is. So if you use that matrix, right, and you calculate P inverse AP for your matrix, then our theory says that what you're going to get is your real eigenvalue lambda 1, your complex eigenvalue lambda 2, and then the complex conjugate down here, right? But the thing is, this is a 3 by 3 complex matrix, right? So that would be complex diagonalizable, but it wouldn't be real diagonalizable, right? But you could find its real Jordan form, right? What should its real Jordan form be? What did you find for your, I'm calling it, what was your lambda 2?
It was plus or minus 2i.
Plus or minus 2i. So let's work with 2i for your lambda 2, right? So that says to me that the real Jordan form for that, what was your real eigenvalue?
1.
So you got 1 for your real eigenvalue. And then you've got a 2 by 2, what did I call it? I guess I called it real Jordan form 2i, right? And so that would be what? Alpha is equal to 0. So you get 0, 2, minus 2, 0. So I mean, there exists, if you you can, I think that's the real Jordan form for that example. I mean, that homework problem. If you were to similarity transform by the change of basis matrix, where the first column is your real eigenvector, the second column is the real part of your complex eigenvector, and the third column is the imaginary part of your complex eigenvector, similarity transforming the given matrix should put it into that form, which is, by the way, a real Jordan form. But no, it is not real. It's not real diagonalizable. I mean, here's a general comment. If you have the real Jordan form, if it contains any interesting real Jordan blocks, even one of those means it's not diagonalizable in the real sense. Because that Jordan block, real Jordan block, speaks to the existence of a complex eigenvalue, which means, again, going back to day one, it's not diagonalizable. Because matrix is diagonalizable over a given field if and only if there exists an eigenbasis with respect to that field for that matrix. Does that help? I probably said too much. It's okay though.
Other? No, I know I did it right. I'm happy.
Oh, good, good. Excellent, excellent. Other questions? So I haven't asked you guys anything about differential equations in this homework? That's the next one? Okay. I don't know if I actually put a day on that in my schedule. Or was I supposed to do that in the last couple days and I forgot? What's in mission 8, I guess is the question. Right? If I can find mission 8, where'd it go? Let's see here, mission 8. Orthonormal basis, projection, perpendicular to a space, closest point, inner product, Cauchy-Schwarz, triangle, linearly independent, inner product. Huh. You know, guys, I'm starting to think, oh, there it is. There it is. In problem 9, mission 9 rather. In mission 9, which is, I guess that's way in the future, isn't it? So the thing I keep feeling like I need to talk about is actually at the very end of your homework, where we look at how to solve the differential equation dx dt equals to ax, where x is a vector of unknowns, using what's called the matrix exponential. And well, I'm not sure it uses the matrix exponential, but I use the, turns out eigensolutions and generalized eigensolutions allow us to solve differential equations. You can solve a system of differential equations, dx dt equals to ax, for any choice of a, through the use of eigenvectors, generalized eigenvectors, and the complex eigenvectors. There's a well-understood path to solve any system of linear differential equations in n unknowns. But anyway, that's apparently my, I think that might be my parting shot at you this semester. Let's see, your mission 9. Is there a mission 10? I don't think there's a mission 10, is there?
I don't think so.
So that's the end of the road. So I can talk about that in any future help session if it's helpful. Yeah, I'm going to do it today. Anyway, we can't do anything else today, right? So.